the work is about some geometric aspects of the 5-dimensional analog of what you would call the Kerr-Newman black hole, charged rotating black hole. And this is joint work with a colleague from Leipzig University and my colleagues from the Institute on Jitna, which whom you may know quite well. Okay, so I prepared the presentation with a bit short notice, so I apologize if there's not so much, maybe there won't be enough details to satisfy everyone, but if you want me to clarify something, please ask. Of course, full details are in the article. All right, so I don't think I need to motivate the interest in charge rotating black holes so much. I think it's a kind of a natural object to study. In 5 dimensions or in higher dimensions, we of course know both spherically symmetric charged black hole solutions explicitly and the rotating but uncharged. Okay, and they have different names, maybe Schwarzschild-Tengerlini or high dimensional Horizon-Nordström for charged non-rotating, and Myers-Perry for rotating but uncharged. So there's no exact solution for the charged rotating case, but there's been some work in literature, for example, by authors around Jutta Kuntz and some of her collaborators, that basically post some ansatz parameterized by a bunch of functions. So this metric in 5 dimensions, so time, radial, polar, and the coordinates corresponding to the rotational symmetry directions. And the ansatz is parameterized by, just a bunch of functions that enter the metric in some way. I never really questioned how they came up with this ansatz, but they did it. And if you plug this into the Einstein-Maxwell equations, you get a system of ODEs in the radial variable for these functions. And so they noticed that you can find solutions, and so now basically shown that you can access the 5-dimensional charge rotating black hole via this numerical solution, even though the solution to these reduced Einstein-Maxwell equations are not known explicitly. And basically what they did is they studied some connections between charges and multiple moments of the solution. That's as far as they went. In the solution of this ODEs that you get, they had to of course impose boundary conditions, which they described as corresponding to asymptotic flatness, which at radial infinity, so some limits of these functions parameterizing the ansatz are prescribed. And also they demanded that the solution has a regular horizon. They didn't really specify so much what they mean by regular horizon. I guess it's kind of understood that it should be, at least the way I understood it, should be it should correspond to a space-time where you can introduce horizon penetrating coordinates such that the metric is smooth across the horizon in those coordinates. But they didn't go into those details. But all right, so suppose that we have numerical access to the solution. Now we can ask some natural questions about its properties. So for example, at least motivated by my colleagues from like Wojciech Prague and Tomasz Malek, a question was to look at the algebraic type. There's a faint hope that if it does have special algebraic type, then maybe there's another way to access the integrability properties of the spacetime and maybe find the exact solution analytically and compare it to the numerical one. There's a faint hope, right? But
let me check, Igor, at the beginning,
yeah.
It has just one axis of rotation. No?
Oh, right. So this is in general 5 dimensions. You have 2 possible axes of rotation. So this specific case corresponds to equal angular momenta. I think if they have different angular momenta, then you reduce to not ODEs but 2-dimensional PDEs. So I think that it's an R and theta.
You don't study this.
They have studied it as well, but it's much more complicated. Yeah.
You know how I was wondering how magnetic field, because there was a magnetic field thing.
So here, that's I mean, there's some magnetic field encoded in here, of course. Yeah. Please.
This notion of asymptotic flatness,
yeah.
If I am not wrong, it had a problem with odd dimensions.
So they also didn't go into much detail in that, but it's not asymptotic. So you think of asymptotic flatness in terms of conformal compactification?
Well, in terms of writing the metric as the flat metric plus something,
yeah,
it's the case at infinity.
Yeah.
But the problem is that I think that for odd dimension, this first term goes with a half.
Yes. Yeah.
Half the dimension.
Yeah, which prevents a smooth conformal compactification. Yes. So this is all present, but I mean, you can introduce this notion of flatness, asymptotic flatness, still for high dimensions. Still, like I said, they didn't go into those details. They just concentrated on getting the equations, getting numerical solution, and studying some global properties of it.
You can do Kershel type code and anything. It's eta in 5 dimensions plus something.
So we, in fact, showed that it's not Kershelled under a small restriction on the null vector. So if a null vector is not geodesic, if null vector is geodesic, then it cannot be Kershelled.
I see.
So that's.
But it can be chosen so that it is Kershelled.
No, not as far as we know. Okay. That's the point. Yeah. Right. So these are the kind of questions one can ask. So in particular, the first thing we tried is looking at the horizon. So like, what can we say about the geometry of the horizon, its regularity, and so on. So the first thing that one can think of is basically try to introduce horizon penetrating coordinates like Eddington-Finkelstein or its analogs or Kruskal coordinates. And we were working with some formulas. There was some problem that came out. And looking into it a little bit deeper, we found essentially the same problem when trying to match the ansatz, right, with all of these parameterizing functions to known solutions which are known to have regular horizon penetrating coordinates, like the charged non-rotating and the charged charged non-rotating or the rotating uncharged cases. And we were able to do this, but along the way we discovered that in these solutions you have the usual regular radial coordinate, which I denote by upright r. It's going to be a little bit difficult to distinguish. I apologize for that, from the Kuntz radial coordinate, which is denoted by the script r. But yeah, so in terms of the upright r's, we know what all these things should be. But when you translate between the regular radial coordinate and the Kuntz radial coordinate, you discover that it has a square root singularity precisely at the horizon. So the way that they wrote the ansatz, their radial coordinate is incidentally happens to be singular at the horizon. So well, then that calls into question whether the solution they obtained really is regular at the horizon or not. So this is what we needed to investigate. Well, actually, so it's one thing you can note that if you move around some factors of the Kuntz radial coordinates, you can group them together with the parametrizing functions in such a way that these combinations are all regular, right? And so, well, what happens if we absorb these factors of R into these parametrizing functions in the ansatz? And this is what we did. So we basically, it's the same ansatz as before, but with different parametrizing functions, which differ by font, essentially. So the translation is here. So these are our functions, parametrizing functions. And on the right-hand side, these are the original Kuntz parametrizing functions. So we grouped things together. And it turns out that it's not only so it's not just we needed to change the radial coordinate, but just for ease of writing formulas, it became convenient to introduce a square of the coordinate, which I write as capital upright R, as an independent variable, and then the equation somehow became easier in that coordinate.
The R equal constant is horizon or not, or it is more complicated?
R equals, there is a constant for which R, that is the horizon. Yeah.
So So you mean, but you know, if R is not 0, so I'm surprised how regularity of M and M times R squared may be different.
So the singularity is here, right? So
Oh, I
R,
see, this is
yeah.
upright versus this.
Yes, yeah.
Oh, I see. Okay,
Yes. So, so in the paper, it's easier to distinguish, but in the presentation, it shows the fonts so that they're they're only different by the slantedness. Yeah. So this is the non-regular ones. This combination happens to be regular. Yeah. Okay, so when you see derivatives written by primes, these are derivatives with respect to the squared radial coordinate, this capital R. All right, so we have this parametrized ansatz, and we rederive the Einstein equations, and they can be presented in this specific structured form, and basically it follows what the the work by Kuntz and et al. Did. So they also structured the reduced Einstein equations in a similar way. But in their equations, this irregular radial coordinate appeared explicitly in many different places. Okay, what we actually found is that after doing our reparametrization, these the structured form of the Einstein equations becomes autonomous in the squared radial variable. So it doesn't appear explicitly only as derivatives. In particular, this means that there's a shift symmetry in the squared radial coordinate. Okay, so that's somehow the equations are look a little bit simpler. And there are three groups of equations. So combining some components, you find what we call conservation laws. So these are some combinations of the parameter functions which are sitting under the derivative, and you can just integrate that and get an integration constant. And this is a way in which charge, angular momentum, and locations of the horizons appear. So in general, you could have like an outer horizon and inner horizon, and their locations happen to be integration constants in the extracted from these the subsystem of conservation laws. So once you have integrated this part of the equations, you can then substitute these expressions into the rest of the equations. So for example, you can eliminate A0, which is the electric part of the vector potential, time part of the vector potential. And you can also eliminate omega, which is the parameter in the metric describing the rotation. And you end up with a 3x3 system of second order equations. And you look at the structure carefully, and you basically notice that, okay, so this is a non-degenerate system of equations. So you can solve for the highest derivatives. And I've written the highest derivatives, second derivatives here for the f, m, and a phi variables. And you can think of this as a second order boundary value problem, nonlinear boundary value problems, but only for these three functions, f, m, and a phi. But on top of that, once you find these equations and then eliminate these second derivatives of all of these functions from the remaining components of Einstein-Maxwell equations, there's still some components left. And they basically can be described as a constraint, as a first order constraint. So when you solve, say, the BVP part of your equations, you need to check that your solution on top of that still satisfies this extra first order constraint. Right? Just question. Yeah. Is the constraint possible to put into boundary conditions? Yeah. Well, so if you think of it as an initial value problem, right? You pick a point, you say, I specify, say, 6 initial data. And then, yeah, so then you have to look for the subset of initial data that satisfies this constraint at one point. And actually, there's another compatibility condition that makes sure that if you solve the BVP, the constraint remains satisfied. So everything is consistent. There's no other integrability conditions you need to find. Right? So this is kind of a well-structured form for the reduced Einstein equations. And at this point, you can once again access the solution by solving numerically, as I just described, the BVP system. and checking that the solution that you find satisfies the desired constraint, and imposing the boundary conditions at the horizon and at infinity. Okay, so what are these boundary conditions? And here we needed to delve a bit more deeply into what it means to have regular horizon and the regular null infinity. So let me start at the regular null infinity. And as you mentioned, that people have thought a bit about how to do it precisely, and the consensus in the literature seems to be that if you can introduce boundary coordinates at null infinity, and such that the metric has a specific asymptotic form, then you can call this metric asymptotically flat. And this method, this is possible to do consistently in any higher dimension. So odd or even is fine. So I'm not referring to a conformal compactification null infinity. I'm referring to existence of a boundary coordinate system. So boundary coordinates consist of radial angular variables and a retarded time variable. And in these coordinates, the leading components of the metric have to be basically, this is the Minkowski form. So the plus minuses correspond to either the future null infinity or past null infinity. And the subleading terms have to have this specific form. So notice that the zeros here are specified, are exact. So all subleading terms also have zeros there because it's part of the gauge conditions for the boundary frame. And the weights for the subleading terms are kind of different in blocks. And that basically just has to do with that, like in the Minkowski metric, you can also split it into blocks that has different R weights, right? So this purely angular block has weight R squared. The RT block has weight 1 in terms of, weight 0 in terms of the radial variable. And by consistency, the off-diagonal blocks, which are 0 here, but by consistency, they would have to have weight 1. And
this R is in some respect numerous at a distance, like it is in Bond's coordinates.
So the radial variable, yeah. So Bondi, I think.
You have this condition on G2.
Yeah. So they impose some condition on the determinant of the spatial part of the metric. You can do this. So we didn't do this because you can. We like our own radial variable. But you can always, there's a unique way to reparametrize to the Bondi radial coordinate if you like, but we kept our original radial coordinate. So yeah, but basically, so that explains the difference between the subleading terms.
Curvature, it's really the case, no? If you have these assumptions.
Yes. So people who introduced this notion, they check that, it results in components of curvature decay in certain ways. And there are many different references, but one we found very convenient, which treated at the same time electromagnetic, Yang-Mills, and gravitational theories, is this recent paper by Satish Chandran and Wald from 2019. The reference is an article, so you can check it out. And we give a small survey of other references that give basically equivalent definitions in our paper. All right, okay. So now we have this the form of the leading term, the subleading terms, and you could expand in inverse powers of the radial coordinate to get more and more terms. So can we build such a Bondi coordinate system for our parametrized metric ansatz? And the answer is yes. So we had to kind of fiddle around with the formulas a little bit, but we found, this way of defining. So this is in terms of differential, but can be quite easily integrated to get a translation between our coordinates and what would be the Bondi coordinates. So then the asymptotic form of the metric and the vector potential imposes the following leading terms, and in some cases some subleading terms, on our parametrizing functions. And at this point, well, what we had to do was go back to basically, the main thing we needed to make sure is that we could consistently solve this BVP at infinity as a power series expansion. Okay, and if you've studied ordinary differential equations with singular points, you know that you can apply this Frobenius method and check what are the consistent powers in which you can expand your equation at the singular, your solution at the singular point, and at what powers of the expansion can you specify free coefficients? Because when you're dealing with singular points, it's not just that you can specify the value of a function in the first derivative. So you need to build an expansion, you need to plug it in, and you need to make sure which of the terms in expansion actually have free coefficients. Okay, so this is what we did. Well, it turns out that you can consistently continue these asymptotic leading terms as a Frobenius expansion of the boundary value problem coming from the Einstein-Maxwell equations. And there are basically two free parameters at infinity. So all the other parameters, so just are fixed either by enforcing the extra constraint, right, this guy, or imposing, making sure that we satisfy the leading asymptotics with asymptotic flatness. Yes, so.
But do you have to assume that the admits expansion in power series, so by this method, or it is not? I mean, because it can have logarithms, right?
Yeah.
So
right. So logarithms are allowed in general in the Frobenius method, but they so the way that they appear, they would contradict the asymptotic flatness assumption. So the coefficients that appear in front of logarithms are eliminated. Yes, that's right. Yeah.
Another thing is that I don't know if you mentioned that and I missed that, but these asymptotic flatness definition does not make the metric 10 to the flat metric. Because you have terms which are regular in the second matrix.
What do you mean?
Oh well, maybe yeah, because they are negligible with respect to what you mentioned there.
Yes, yeah, you have to combine them somehow. Yeah. Okay, right. So the point of this part is that after applying the Frobenius method, we have determined that the general solution that of the Einstein-Maxwell equations in this this reduced form that satisfy the asymptotic flatness conditions, really in the strong sense that there are this Bondi coordinate at infinity, which satisfies these leading asymptotics. So there are two free parameters on top of the integration constants corresponding to a charge, total angular momentum, and the locations of the horizons. Okay, all right. So just keep this in mind. So there are two free integration constants when you solve the boundary value problem in asymptotic series at infinity. Okay.
Additionally, to the parameters which label charge,
yeah,
momentum, and mass.
That's right. Yeah. So just recall that once you integrate these conservation laws, then charge, angular momentum, and these radial constants enter as external parameters into the BVP. Right. So the BVP has you see J, Q that appears here explicitly. So the solution space of this, having fixed these parameters, what I call external parameters, is 6-dimensional, of course. So out of these 6, 2 remain free while satisfying the regular null infinity asymptotics. Okay.
So sorry, why is R plus and R minus independent?
So it so happens that this particular parameter, when you extract it from the corresponding equation from Einstein equations, is just satisfies this conservation law, and then general integral has this form. So I mean, it's a second order polynomial in this capital R. And just suppose we are interested only in those cases when it factors with real roots, and then the larger root is where the outer horizon is located.
Just somehow come to the physical parameters, and usually is R plus and R minus are related to mass and momentum.
Yes, they are.
Yeah, and here.
Yeah. So right now
they are independent. There is one more.
Well, so it turns out, and I will get to this, so that the mass parameter actually appears as a free as a free integration constant here. Well, we will later essentially interpret it as a mass parameter, but the external parameter at this point is these R plus R minus constants, and once they are fixed, I will show you that the solution is fixed uniquely. So then that creates a relation between R plus R minus and M, and that you can invert, and then you can specify the M.
So there will be some.
Yeah. Of course, I can't tell you what they are explicitly. It requires solving the system. All right. So then we undergo exactly the same exercise at the horizon. So if you might recall that this is the point where we started. So we were looking for horizon penetrating coordinates. Like Eddington-Finkelstein type, or if you wanted also to cover the bifurcation point where the past and future horizons meet, you needed some analog of Kruskal coordinates as well. And you wanted to make sure that your metric is parameterized in such a way that in, say, Kruskal-like coordinates, it is its components are smooth on both horizons and also at the bifurcation point. So it took again some playing around with formulas, but we found a way to express Kruskal-like coordinates in terms of the coordinates that we start with. So I give you the final formulas, but in the paper we give some derivation of it as well. I should mention that there's a small literature on trying to come up with what some people call double null coordinates, global double null coordinates on black holes and high-dimensional black holes, including Kerr and so on. Ours was not such an ambitious aim because we didn't necessarily need global double null coordinates. We just needed double null coordinates in the vicinity of the horizons. And this choice is much simpler than some other expressions you find in the literature, but it's not so ambitious. It only needs to satisfy those properties near the horizons.
And when you say near the horizon, you mean that you have again only some expansion, or you have really some formula on neighborhood of the horizon?
So the formula is this one. So the only thing that's not explicit is that there's some function here which is smooth in our radial variable, tends to 1 at the horizon, and there's some formula, some differential equation for it you can write down that basically has a unique solution. Otherwise, that's it. That's the formula. So this is constant. So this is our rotation parameter function evaluated at the horizon. So sometimes I'll change the notation a little bit. So our H for me is the location of the outer horizon, and R plus and R minus are the constants that appear in the integration of this one of the conservation laws. But I usually set the location of the horizon to be R plus, which is the outer root. All right, so basically when you translate this regularity property, so basically a smooth Taylor expansion at every point of the horizon, including the bifurcation sphere, and then you get these asymptotic conditions on the parameterizing functions, where for briefness denoted by rho this difference here, okay, which is 0 at the horizon. And then you can go and do this Frobenius expansion again, and once again discover that yes, indeed, you can have an expansion in integer powers of R. If there are logs, they contradict this smoothness assumption and they are killed. And once they're killed, the remaining free parameters appear in the following locations. Okay, and again, the external parameters appear here. So there are 4 free integration constants in the BVP system of the Einstein-Maxwell equations. Okay, so any questions on this part? I hope it's good. Yeah.
You have a mass parameter in your equation, right?
Well, not yet. So far I only have these parameters. So yeah. By the way, so these leading constants in the Taylor expansion are fixed by solving the conservation law, right? So I solve this. I solve these equations for A0 omega. I know what they have, what expansion they have at infinity. Okay, and knowing this, I can solve the full system, extrapolate back to the horizon, and at the horizon, that knowing those asymptotics at infinity fixes these constants. So these are fixed by external parameters.
Oh, that's what I do not understand. If you start at infinity,
Yeah.
are you guaranteed that you end up with regular solution at horizon? It is due to constraint, or how you are sure that you won't have diverging one?
Well, so so here it comes to the point, well-posedness point. We now have two families of solutions. So those that are correspond to a generic solution satisfying all the properties we want at infinity, and the generic solution satisfying all the properties that we want at the horizon. And the one at infinity is two-dimensional. The one at the horizon is four-dimensional. And they're sitting inside the six-dimensional solution space of the BVP. So the well-posedness comes down to the fact that a two-dimensional subspace and a four-dimensional subspace in a six-dimensional space are generically transverse. So they would intersect at a zero-dimensional space, so 1 point. It's usually 1 point or maybe several points, but generically 1 point. And that is the uniquely fixed solution of the boundary value problem. And because it's obtained in this way, it must satisfy the regularity conditions at both ends. So this is the sense in which the Einstein-Maxwell equations are well posed. And of course, for nonlinear equations, you can have weird things like these two families don't meet at all, or they meet but in several points. But that is a kind of very special situations which you would see from the convergence of the numerical scheme if you use one. So if it never converges, probably means that there's no solution at all. If it converges in to different things, starting from different initial conditions for the iteration, then it means that there are multiple solutions. But in our experiments, we just saw that there's usually just one solution, and you arrive at it pretty in kind of stable, quick way. Right, and so the last thing I just wanted to mention about how the solution is really determined by the external charges, which now include which can be taken as mass, angular momentum, and charge. So the angular momentum and charge are already appearing as external parameters in the BVP system that we're solving. But like I said, instead of the R plus external parameter, which appeared there explicitly, we want to use the mass to determine the solution. So what happens is with J, Q, and R plus fixed, you find the solution, and from that numeric relationship, you have to invert it to make sure that you have the right mass. So you allow yourself to vary R plus until you hit the right mass. Yeah. Right. So I should also say that because of the R autonomy, so the shift symmetry in the capital R variable, you can shift actually the values of these integration constants R minus and R plus squared.
What I'm confused. You are saying that you have symmetry in shifting.
Yes.
R.
Yeah.
Isn't the curvature somewhere diverging or something like that? Don't you have some special point?
Well, yes. So there's some point that corresponds to diverging curvature, but that will also shift.
I'm want to the more basic question I probably was not sleeping. There is a relation between capital M, J, and Q, like in normal black holes or not?
Oh, you mean there's some inequality?
Yeah.
Yes, and so those relations were actually explored in the original works by Kuntz et al.
I see.
Yeah.
But you can also construct without problems naked singularities, although your boundaries on horizons. If you change them.
I guess the naked singularity would correspond to having imaginary R plus and R minus. I guess you could do it, but we didn't look at that case.
But you will see that, for example, then mass will be less than whatever combination of J and Q. Maybe.
So yeah, we didn't look at this. I think maybe.
And this J is just this one rotational parameter.
Right. So it's the value of two rotational parameters which are equal. Yeah. Yeah. So let me just recap a little bit.
Problem still. I mean, these are trivial questions, but to include magnetic charge.
That would require slightly different asymptotics on the vector potential, I think. Right, because it would. So the asymptotics on the vector potential, I think they exclude. Oh, yeah, that's right. Yeah, but I think also, I mean, if you were to think of something like magnetic charge, I think it would appear the different order.
You mean F and F star or whatever?
There's a different number of components of electric magnetic fields in 5 dimensions. Okay, so but just to reiterate this point about the external parameters. So here we have 4 integration constants that appear as external parameters in the BVP, but the whole system is R autonomous. So any solution when shifted in R squared is still a solution, and that is obviously a diffeomorphism, right? So geometrically, these are not different solutions. So we're allowed to use this residual gauge symmetry shift in R squared to shift it to any value that we like, right? So we like to set R minus to 0, right? And that leaves 3 parameters, J, Q, and R plus, and then we use R plus to parameterize the mass. So now we can use M, J, and Q as the external parameters, and by the well-posedness, they uniquely fix the geometric solution. And here is a plot just to illustrate that it is indeed possible to solve the boundary value problem, for some random values of the parameters. So the details are in the paper. How to read this figure exactly? So these functions that appear in the BVP system, they're in fact the way that they're plotted here, they're rescaled by some powers of the radial variable. But what you can see clearly, if you notice that the plot of the x-axis uses the inverse radial variable, meaning that the horizon is at 1, infinity is at 0, and this is now the internal part of the black hole, and so R minus is at sent to the point at infinity here, so that would be the internal horizon. And if you wanted to go to the point where there's the curvature singularity, you have to go to negative values of the inverse radial variable. Okay, so what?
Remind me, what is this A5?
This is
the sign inside and outside.
It is the phi component of the electromagnetic field. Yeah, and it may be rescaled by some power of R minus RH, but it just has convenient scaling. But once you unscale everything, they're smooth and have finite values when this
potential, not
vector potential. Yes, yeah. So I just wanted to highlight that. So far I've only been talking about the boundary value problem on between the infinity and the horizon, so which corresponds to this interval from 0 to 1 on this plot. And if you denote by the bold curves solutions obtained in just for those intervals, and I have to credit my co-author Markus Froeb on writing some Chebyshev polynomial iteration scheme that did this. So you have some approximate expression or polynomial approximation in this interval. You can of course extend past the horizon, because now the solution is not singular at either the horizon or at infinity. And if you extend it past the horizon, you can use the extension to seed a normal ODE solver to solve the three-dimensional 3x3 second order system in the internal direction, and you can denote that by a thinner curve. And what is illustrated here is actually kind of the stability of the extrapolation of the outside solution into the horizon. So the matching is done like somewhere very close to the horizon inside, but you can see the two curves stay close together for quite some stretch inside the horizon. So I think this shows that taking the asymptotic structure of the solutions at the horizon and at infinity stabilizes the numerical method in some sense.
But you can continue towards the inner horizon or not?
Yeah, so the inner horizon here is at infinity, and yeah, you can solve the ODE as far as you like.
The structure of space is so that it is again time dependent, or the Killing vector changes slightly? No.
I think that the kind of geometrically the structure will be very similar to what Kern-Newman has. So I don't think
the Killing vector should change. From
yeah. Yeah. Okay, so I think this is just to show that we can practically use the information that we obtain with this theoretical analysis to have kind of like a robust access to the numerical solution for the ansatz.
Yeah. How much it tells about regularity just of coordinates or the solution? Because if you ask the same question between horizons,
yeah.
If you study the regularity of one horizon and regularity of inner horizon,
yeah.
so you will get different conditions.
Maybe, yeah. So this solution, so this solution is not guaranteed to be regular at the inner horizon. We didn't demand this, so it's quite possible that it blows up at the inner horizon. We don't know. We haven't checked.
It should be unstable if four-dimensional picture is correct.
Sure.
In any case.
Yeah.
Unstable in dynamic sense.
In dynamic sense, but here even yeah, without any matter or radiation.
No, you have to perturb it.
Yes, but this one could be quite clearly the right one and regular.
It could be, but we don't know. We haven't checked. Yeah, but if you demand that the solution is regular at the inner and outer horizons, then there's no guarantee that it's going to be the same solution as the one that is regular at infinity and outer horizon. So there could be a mismatch. I mean, in 4 dimensions, there happens to be no mismatch, but I don't see a generic argument for why that would be the case.
And this is only question that we have to use different coordinates in different regions, or is it statement about a real solution that it cannot be extended to
yeah, whether the outer solution can be extended to the inner horizon. So it's not. I mean, our analysis doesn't answer this question, so it's an open question in a sense.
The inner horizon doesn't exist at all.
But I don't see how it could. Yes, some.
So at the inner horizon, you can basically do an analysis that looks like this. And I imagine maybe you have similar structure for the unfixed parameters in the expansion. So maybe there will be another 4-dimensional space, and then you have these two 4-dimensional spaces meeting inside a 6-dimensional space of solutions. of the BVP. And then you could have some freedom in terms of adjusting solutions that are regular at both horizons. And maybe, there will be enough freedom to choose the one that is also regular at infinity. But this is speculation, right? So I don't know. Well, we proved that it has regular null infinity, and it has a smooth horizon. So
no, I was thinking.
And the horizon, of course, killing horizon, right? Because it has a killing.
So no, I was thinking, when you were doubting what will happen if you extend through the outer horizon
Yeah.
inside, and you find their singularity. So, but you do know that the singularity would not be seen at infinity.
Right. Yes. Yeah. Okay. So I think that's basically it. The only other thing that I want to say is that we also, use this theoretical analysis of the reduced Einstein-Maxwell equations to eventually study something about the algebraic type of the black hole. And once you have the coordinates regular on the horizon, then you can just plug the metric into Mathematica and ask, what is the Weyl tensor at the horizon? And turns out that at the future and null horizon, one of the du or dv coming from the crucial coordinates is a principal null direction, or so Weyl aligned null direction. That's the terminology you have to use in higher dimensions. And the Weyl tensor happens to be of type 2, both on future and past horizons. And when they meet at the bifurcation sphere, the algebraic type specializes even to type D. And so both du and dv are ones in that case. But as soon as you go outside the horizon into the bulk towards infinity, you find that it is not of type 2 anymore. And this is, of course, it's complicated to check whether a metric has certain algebraic type or not. It's difficult to demonstrate that it really does not have special algebraic type. But Tomasz Malek did a very careful case-by-case analysis. So writing down the 5-dimensional versions of Bell-de-Bever criteria for type 2. And then even without using Einstein equations. So you went case by case, said, okay, if this is satisfied, then it could be type 2. If this is not satisfied, then maybe some other condition you could check. And he has a list of conditions and he checks one by one. And basically it never happens that the spacetime is type 2 unless it's one of the solutions that we already know, like the uncharged or the non-rotating case. And in a few cases, so he got to some condition that was essentially also like a second order or first order ODE on the parametrizing functions. And by looking at it at first glance, you don't know whether it's compatible with Einstein-Maxwell equations or not. And in those cases, what we did was we used the Frobenius expansion at infinity, expanded to order inverse r to the 5, and checked that this produced an inconsistency with the conditions required by type 2, unless you reduce to one of the known type D cases. So that's it. So in the paper we wrote that the metric is of algebraically general type, but now it actually escapes me why we didn't say that it's at most type 1. I'm not sure. So maybe my colleagues, if they call them to talk about this work, will make the right argument. But that's what we wrote. Yeah, so this was also related to another no-go result, which was the possibility of writing the metric as in Kerr-Shield form, and using some proposition that was proven by my co-authors sometime earlier, and combining it with no type 2 result in the bulk, they could conclude that it's definitely cannot be Kerr-Shield with a geodesic null vector k. I think that we didn't arrive at a conclusion for most general type of Kerr-Shield, but in my understanding, the most common one is where k is geodesic. Okay, so I think that's all. So with that, I thank you for your attention.
So thank you very much, and sorry for the not so successful beginning from my side. And now questions in the lecture room first. Jahanur?
Mass parameter satisfy any conservation equation? Can we just go? I mean, can you just go back to the Bondi one coordinate transformation?
Yes.
In the function f, the one minus
Yeah.
had by r.
Yeah.
So usually 1 over r piece is the Bondi mass.
Well, that's yeah. So basically, why do we call this parameter mass? Well, it turns out that you can take the formulas for ADM charges, and you can plug in this expansion, and the value of the mass will equal exactly that parameter.
Yes. So my second question is that usually in Bondi set coordinate, the mass parameter satisfy a conservation equation. I mean, usually satisfy a mass loss formula, and that is related to the subleading part in your metric, in your angular part of metric actually. And that should be related to, to compute in Bondi set coordinate del u m. That should be related to the
well, so you're thinking of the case where m depends on u.
Exactly.
Yeah, well, this is static, so there's no u dependence.
If you look at your metric that is subleading term in order r0. So when you write your metric at g mu like r square sine square theta.
Yeah.
And plus
this one.
r0.
So, by the way, these asymptotics that I wrote down are for the static case. So without, stationary. Yeah, stationary case without radiation. So I think with radiation, you do get some fractional powers here. Yeah.
With radiation, I think, you may get order r.
Yes. Yeah. But yeah, I made sure to check there's no radiation. Yeah.
We started with this ansatz of Kuntz, etc.
Yes.
So this is done for other black holes with higher dimension, or it's just specifically for?
I think they do have some ansatz for higher dimension ones, but they're even more complicated. And yeah, so 5 dimensions seem nice and accessible.
They are able to make the analysis for differentiation.
Yes, I think on the condition that instead of ODEs, they get PDEs and R and theta, which of course makes numerical analysis more complicated.
So here you have concentrated on the Einstein-Maxwell case.
Yeah.
So it would be interesting to do other cases. So the simplest one would be Einstein-Maxwell Jen-Simons, where the exact solution is known, and you could compare to your numerical solution. But then one could go also beyond Einstein-Maxwell and be some conformal electrodynamics and dimensions. So would it be difficult to just change the equations? And
so the most difficult part was basically getting the Frobenius analysis right. Well, I mean, once you found the right combination for the asymptotic coordinates, then the most challenging part was getting the Frobenius analysis correct, because it's a non-linear equation. It's a little bit complicated, but basically it's not immediately clear which terms in the equation will contribute to the part that determines the characteristic roots. I wrote the system specifically in a way that all the terms that you need are on the left-hand side. So, but they needed to kind of do this analysis carefully. But once you know what terms you need, you just do the linearization, you plug in the leading terms, then you find this characteristic matrix and you look at its eigenvalues. So that part, yeah, you can do it when the equations are different. This structure of conservation laws, boundary value problem, and constraint may also change for other equations, right? So this was specific to Einstein equations, but for other equations, if you can put them in some form where you get a determined system, then that determined system you can analyze exactly in the way that we did.
So
change from the Maxwell equation, or equation from the formatic is the same?
Well, they would have like,
yeah. Right.
So here only this equation would be modified, maybe this
So
one.
you say, David, there is explicitly known Maxwell, Simon, and Einstein.
Mhm.
Why it's somehow coupled together so that you cannot switch off the Simon?
Yeah, and I think that solution is type D,
Yeah,
right? So
maybe, I don't know.
yeah, I think my co-authors kind of checked that at some point.
It's definitely very nice, but
Yeah.
but it's like,
But it's also explicitly known, so the value of this analysis is
So what
questionable.
happens if you put something which corresponds to Maxwell equal to 0, the Chern Simon also disappears. Or sorry, if you put Chern Simon equal to 0, so Maxwell disappears. Because it was somehow fortunately coupled together that this solution is known, and here it is not.
Yes.
well, there's a specific coupling for the Chern-Simons term, so it's not a general one.
Yeah.
Really.
To Maxwell.
I'm not sure whether can we switch off continuous.
No, you cannot.
Well, not while keeping the exact solution, in my understanding.
Any online questions? If not, so thank you, Igor, once more.